Hello everyone, welcome to my first video of a series of introductory level algebraic geometry. Now this is a topic that's very fun, but also really abstract. So I'm very excited to actually get into it today. In this video, we're not going to do anything too fancy. All we're going to do is establish some essential definitions of algebraic geometry. And in the next videos, we will be proving some things and working with those definitions. So, without any more further ado, let's begin. So what is the scope of algebraic geometry? Well, algebraic geometry studies the zeros of polynomials. Now, if you guys have taken Algebra 1, you probably already know what a zero of a polynomial is. You might say that this is actually quite boring, and how could studying zeros of polynomials be anything exciting or abstract? Well, the thing with algebraic geometry is that it takes the idea of zeros of polynomials and abstractifies it. It uses methods from abstract algebra to kind of generalize the notion of a zero and to just do stuff with it. So this topic is pretty historical, in the sense that it started off with just literally just trying to find zeros of polynomials. Like, for example, the quadratic equation helps you find zeros of polynomials of order 2. So there are other functions that are a bit harder to solve. There isn't a simple equation to solve it, to solve for those zeros. So in that sense, we'd have to employ algebraic geometry to help us find those zeros. So let's begin. First of all, let's just start off with some prerequisite material first. So let's define what a field is. Now, a field is one of the core essential concepts of algebraic geometry. And a field is just basically a group with addition and multiplication defined on it. So take a group, if it has addition and multiplication defined, great. That's the first step to being a field. Second, so this is like number 1, here's number 2. It has to be distributive of multiplication under addition. For example, this is like a times b plus c just equals ab plus ac. So if I have addition here, I can distribute the thing that I'm multiplying the second term by ab plus ac. Now, you might ask what a group is. Now, I've already made many videos on group theory, so I recommend checking out my group theory playlist if you want to know what a group is. The group here does not mean like the colloquial set of objects. Groups mean something a bit different in group theory. So yeah, just watch that video if you don't know what a group is. And now at this point, you can probably see why we care about fields a lot. Since fields have all the cool, interesting, very convenient properties. Since look, they're groups, right? Groups under not just addition, but multiplication. So I can take a field, I can add any of those two members, multiply any of those two members, and I won't get something outside of that field by definition, right? And also, we have that nice distributive property. We don't have to worry about getting expressions where we can't actually distribute anything. So this property is very convenient, and that's why we study fields, because they kind of capture all the cool abstract notions that we use in normal day-to-day math. Now, there are some types of sets, or should I say groups, that aren't fields, and those are the really nasty ones that we will encounter later. But yeah, fields just capture the really nice properties. An example of a field that you guys probably guessed are the real numbers, right? Real numbers are groups under addition and multiplication, because they're closed under those two things. And they have the identity elements for addition. That's going to be 0, of course. And yeah, so the real numbers are a group, and they're also distributive of multiplication under addition. So yeah, that's an example of, sorry, real numbers are a field. So yeah, that's an example of a field. And there are other fields that we can devise with these axioms. But let's put that aside and get into some more definitions. So let K be a field. Okay, so K is a field. A to the n of K is going to be defined as the Cartesian product of K with, the Cartesian product of K, with K and n number of times, where K is just some positive integer. So A of K just is Cartesian product of K with K. Sorry, ignore the blurb here. K with K and n number of times. So basically, I'm taking K, Cartesian that. I think that's should be an X, right? Or so plus. It's an X. So K, product of K, product of K, just some n number of times. That's what we call A and K. And A and K, like that's what A and K is, but we call N A K. We call that the affine n space over K. So if you're ever reading a textbook on algebraic geometry, if you ever hear affine n space over K, that's what it means. Just take K, Cartesian product it with itself a bunch of times. That's, you get an affine n space over K. All right, now let's define point. Probably wondering, why are we defining point? You'll see why. So let's define point as a member. I think my pen is dying, but point is going to be a member of this affine n space over K. And let's define a1 of K as an affine line, a2 of K, affine plane. And yeah, so these are our core definitions. So let's kind of de-abstractify it. So again, let's give an example of a field. An example of a field is just a specific example are the real numbers, right? Let's just choose R2 for fun, okay? So R2 would actually be an example of an affine n space over K, right? Since R2 is defined, that's an ugly R. R2 is defined as the Cartesian product of R and itself 2 times. So A2 of R is just the R2 plane, right? So R2, the R2 plane is an affine plane, and a member of the R2 plane is a point. So that's like where these ideas are coming from. Because oftentimes like in books, like, we have all these abstract definitions, but it's always nice from time to time to relate it to something more concrete. That's just an example of an affine n space over K. K here being the real numbers, and n here being 2. All right. So what is next? Okay, so let's define what a 0 is. Okay, so we say that a point P, where P is just a1, a2, all the way to n. Let's just want to make this really general abstract. So a point P that is a member in the affine n space over K, pen is almost dead, we see that it's a 0. So the point P is a 0. This is a very crucial term in algebraic geometry. It is a 0 of some function. Okay, my pen, okay, almost dying. It's a 0 of some function f. If f of P equals 0, And f is just some function that is a member of a(n) of k. Okay, I hope you guys can read that. My pen is like, the ink is almost dead, as you guys can see. But I hope you guys can see that properly. So a point P in a(n) of k is a 0 of f if f of p equals 0. F is just some general function, and f shouldn't be a member of a(n) of k. I believe f is just some subset of a(n) of k. All right, I have to get I have to get another pen because mine is dead. So I'll be back shortly. All right, back with some more pens. Okay. So again, here's a point, and a(n) of k is 0 of f, where f is a function if f of p equals 0, where f here is a subset of a(n) of k. Okay, so why is this the case? Again, let's go back to R2. R2 is a really nice field to fall back on if we're losing our comprehension. So, okay, so here we'd have a point P, when it would now be xy. Well, not xy, it would actually just be x in this case. Point P, well, yeah, it would be xy. So your point P equals xy in a(n) of k, that's just going to be the R2 plane, is a 0 of some function f if f of p equals 0. Okay, so this of course implies that y is going to be 0. And this makes sense, right? Since for example, say I have some function y equals x squared minus 2. Well, x is going to be a 0, or the point x0 will be a 0, since that's what you get when you set y to be 0. If f of p, if f of that x gives you 0, that x is said to be a 0. And we can of course solve for the second order polynomials, so we can solve, since all we have to do is just add 2 on both sides. You have 2 equals x squared, and then x is the square root of 2. Right? Yeah, x is a positive or negative square root of 2. And x would be our 0, or it kind of depends on who you're talking to. Some people say that this is the 0. Some people will say that this is the 0. It just depends on your setting, I guess. But you can call either one of those the 0 of your polynomial. Because that's an example of this definition being applied in real life. Well, R2 isn't real life, but you guys get the point, right? All right. Okay. So what is next on our list? Okay, so another definition. So if f is not constant, and the set, we have a set now, the set of all zeros of f is called a hypersurface. Hypersurface defined by f. All right. Okay, so let's give an example again. We have y equals x squared minus 2, and the set of zeros would be x equals square root of 2 plus the square root of 2, then x is minus the positive square root of 2. So you could just put this in a set, right? 2 minus square root of 2. And x, y is our function y is of course not a constant, and this is my set of zeros. So set of zeros is the hypersurface. So this is going to be the hypersurface defined by f, which is just in this case y of x. Or you could also say it's the hypersurface defined by y equals x squared minus 2. So that's what it means. It's the set of zeros. And we call the affine plane. This is just terminology here. We call that the hypersurface. The hypersurface in A2K. A2K, hypersurface in A2K is called the affine plane. Alright. And also, the hypersurface is sometimes denoted as V of F, by the way. If you see V of F, that's what it's referring to, the hypersurface. Okay? Now, if F is a polynomial, by the way, F has to be a polynomial if I didn't say that before. F, doesn't have. Yeah, F usually will be a polynomial, since we say the zeros of polynomials. So if F is a polynomial of degree 1, V of F is said to be a hyperplane in A and K. Okay, so here we have affine plane is a hypersurface in A2K, right? So a set of zeros for R2, for example, would be called an affine plane. However, if F is a polynomial of degree 1, V of F, the set of zeros, the hypersurface, is said to be a hyperplane in A and K. So polynomial of degree 1, example of that is just y equals x plus 3. Degree just means like the highest exponent. So y equals x plus 3. The zeros of that is going to be, well, there's only one zero here. It's going to be x equals minus 3. So this is the hypersurface, and this is a hyperplane in A and K. And when n equals 1, we call this a line. We would call the hyperplane in A1 of K, which is just R, a line. Wait, this was a bad example. Sorry about that. Because A1 of K wouldn't contain R2. That's A2 of K. It would just contain R. So we have the real number line, and then some zero of some function defined on the real number line. Some polynomial, zeros of polynomial, that's of degree 1, we would call that a line. So that is all the terminology of today's video. And I don't know if I'm gonna continue this series. Just let me know if I honestly speaking, I don't really enjoy this subject very much. I am more into group theory, ring theory, QFT. But if you guys like these kind of videos, I'll make more of them. So just let me know in the comments. So yeah, have an amazing day, stay safe, and see you guys later. Bye.